Yeah. So unfortunately, Nick couldn't be here. He had a couple tragedies personally, and it, you know, he was planning on coming, but after these two tragedies, you know, it was too much. So he prepared these slides. We also work closely with JSC. I've been working. I'm actually an IPA to NASA, so I'm kind of part NASA employee. So I get to put my NASA hat on for part of the talk. And we have been working with them for about 4 years on humanoid and exoskeleton work, so it's at least appropriate that I'll be presenting Nick's work. So this is Valkyrie. It's 44 degrees of freedom. It has a battery, so I'll say we, even though I wasn't part of the JSC Track A team. We're thinking about the finals when we designed this, so that's why it has a battery, even though tetherless operation was not required for the trials. It's got plenty of computing power, redundant IMUs, and tons of sensing. I won't go through each of the sensors, but the idea is that this thing was overloaded with sensors. It wasn't clear what sensors we needed in order to accomplish a task, and we didn't want to be limited by, oh, I wish we really had a camera here, I wish we had some IMU information. Or if you look at the feet, they're pressure sensors, accelerometers, and load cells. So it's definitely redundant sensing, and maybe we can get away with one and not the other, or see how we might use for error checking. Maybe a sensor goes bad. So that was kind of the idea of why all the sensors. So this shows how modular it is. In about 10 minutes, a team can put it together, from bolting the arms on to bolting the legs on. And that's great from a number of points of view. One is, transportation. You can take it apart, put it in separate boxes, and transport in about 5 boxes, similar to Robo-Simian. And also from maintenance point of view, you can easily take it apart. You can also have spare, you might have a spare arm, as well as you can do benchtop testing. So we had a torso simulator that you could bolt on a limb and test that limb independent of the robot. And that's a really important part so that you can troubleshoot your hardware. The worst is that you have a piece of hardware and something's not working and you're not sure why, and you don't have a good debugging routine without trying different hardware and seeing what's going on. So this is kind of a timeline of the development. From October 12th, the design started, so it's about 3 months for each phase. And it was a clean slate. It wasn't like we already had a humanoid, although we did have Robonaut 2, but this is a clean slate design. We were inspired by what Robonaut 2, as well as some of our exoskeleton work and the actuators developed for that were, but we just leveraged that technology but didn't, place it into this robot. So it was a clean slate design. There are about 35 designers working on the design of the robot. If any of you have done collaborative work with people, you know that 35 people designing a single robot is a challenge. It's probably not as effective as having 10 people work for 3 times the amount of time, or whatever works out. The math, you can't just throw more people at it and expect it to take that amount shorter. So we actually also used Confluent. We used Atlassian tools. We used Confluence to document everything and have a great way that the designers could communicate where they were in the design phase. So about 3 months for the design, which is, if you design robots, it's a really accelerated design phase. 3 months for fabrication, 3 months for assembly. So right at about July, the robot you can see is a skinned robot that the assembly, the checkout is starting. But we also spent a lot of time looking at the soft goods. It wasn't clear that there was going to be an overhead tether. We wanted to make sure that the robot would survive a fall, so we designed the soft goods. There's vacuum-formed pads. There's a ton of soft goods and pads that will protect the robot if it does fall. And that's probably one of the big lessons. If we could go back in time, we would stop right here and say, okay, check, robot done, start moving this software development phase up to here, and not put our resources on the external skinning of the robot. Then there was a government shutdown on October 1st. It was 16 days, which is, you might say, oh, it's only 16 days, except once we then spooled back up, we had to get all the contractors spooled up with payments, so it basically took a month out of development. By November 1st, we could start development again. So if any of your teams, if we went and said, okay, October 1st, just stop working and we'll tell you sometime in the near future when you can start, but it's actually illegal for the civil servants to work. So it was a pretty tough challenge, having that right at the, so close to the trials. Sorry. There we go. So in order to accelerate development, we split the robot into the top and the bottom so we could have parallel software development. So here we are doing the manipulation. You can see in the upper left-hand screen is the user interface, and the operator is identifying the drill and defining the grasping points or the block and the valve and how to manipulate the object. And then we could now, that was great that we could split the robot into two so that we could have this parallel development. So it did try and help us buy some time in recovery from the shutdown, but of course it wasn't enough. Our walking algorithm was really basic. It was basically static walk, maintaining the center of mass over the support polygon. Pretty slow and methodical, all position control based. So even though the actuators were capable of force control, we didn't take advantage of that capability. In fact, we eventually pulled the springs out to increase the stability of the position control so that we didn't have to struggle with that instability. So we're getting some basic walking. And then finally, full robot testing in about the third week in November. Happy Thanksgiving. So there's about 2 weeks of development left, and now we can put the robot together. So the expectations, were pretty stressful. We shifted to 2 shifts per day, so kind of with an overlap of a few hours. So people had to invert their schedules. Kind of tough on families, but required to try and make progress. So we're doing some basic balancing and getting some walking. So at the trials, we had a self-imposed networking issue that prevented us scoring any points. So we made a software change that, of course, we tested it out in the garage, but that didn't include the bandwidth shaper. So everything was great. We went out on the first day of the trials. Unfortunately, our first day was the easy day. That's the day where we anticipated to get points. In our practice, we were able to get 6 to 8 points. We kind of also did, just like IHMC, did mock trials, and we got, we expected like 6 to 8 points. So that's what we scored previously. So we went out to our first task and then nothing. We couldn't communicate with the robot. It turned out that we were having just a blocking issue. This feature that we introduced in the code was blocking any software commands, blocking the data from the operator to the robot. So we finally fixed it at the last event on the door. The next day was the harder day for us, was the terrain, the ladder, and the vehicle, which we didn't intend to do. And so there we were. Had it been the other way around, we probably would have encountered those problems. And now speaking as IHMC, our ladder task, we're just kind of doing out there for fun. We didn't anticipate doing the ladder, but we found a networking issue hardware-wise that helped us. Unfortunately, that was our first day, and so our ladder task, it ended up getting delayed, but we were able to find that bug before our major day, which was the second day. So again, it highlights the importance of testing, especially under the real-world conditions. Now I'll kind of put back on my IHMC hat. So IHMC has a National Robotics Initiative with NASA to do avatar or humanoid avatar developments for co-exploration of hazardous environments. So it's basically a goal for NASA is to have a humanoid robot that might assist in space exploration. And we are working on the controls for that and using Valkyrie as the platform. So we recently had Valkyrie visit IHMC. So this is our robot lab. And you can see we're working, so this is now at the low level as we're now fully shaking it out, finding some hardware issues or working, talking to the sensors. So it's a kind of a full integration, just like a repeat with what we did with Atlas, but even lower level, where Boston Dynamics took care of all the controls to the joints. We're even going down to that level. So it's pretty exciting for us. What it forced us to do is take our software and make it robot agnostic. So we extracted out what was robot specific and tried to keep a layer that's general. And that is kind of right here is kind of a map of our code. So you got a robot. We have general code that all robots, but I'll be more specific is to say humanoid robots sensor processing networks, data estimation, whole body control, high level. Those are all general to all of our humanoid robot operation. We then pull out robot specific. The hands are pretty specific between Atlas and Valkyrie, so that's kind of why it isn't robot specific. And then the parameters, of course, where your joints are and how many joints you have and your degrees of freedom, and then your sensors. But once all this is handled in our general code, like our operator interface doesn't care what robot you're controlling as long as your sensor information comes in, your point cloud maps, or your cameras, you now are just controlling a humanoid robot. It doesn't matter which one. And so that's a huge software effort for us to extract out the two, what is robot specific and what is general. Here's kind of our development cycle, and it turns out Atlas and Valkyrie kind of share the same development cycle in terms of how much effort it takes or development time to get through the different milestones of operation. So with Valkyrie, we're at about walking roughly, kind of basic walking. Stable shifting about kind of around 11. Walking over flat ground is where we are at Valkyrie, and Atlas we're farther along. But eventually, we're going to push Valkyrie and Atlas and keep this progressing forward. And as we get access to other humanoid robot platforms, we'd like to add that to our kind of verify that our controls are robot independent. So here we're just doing this is kind of our, a daily shakeout where we'll move the joints around under force control, confirm that all the actuators are working, that our controller is working. So it's almost like a unit test for the hardware. Unfortunately, it's not automated. It requires the operator to execute it. But we are working on automated unit tests for the hardware where we'll have a cinder block and a valve and another item that we have to pick up, and we'll basically want to just pop the robot down, hit go, and have the robot complete that task. And if it does, then that's kind of our unit test for the hardware, end to end. And we're close to getting to that point. So here are some of the first few steps. You can see, just as with Atlas, we get shakies. Of course, the nature of it is different, and it's another series of probably 10 issues that cause those shakies that we work through one by one in a kind of a slow, methodical process. But we're able to get stable walking with good center mass shifts and under force control. So whereas the previous walk you saw was position-based, this is using our instantaneous capture point and momentum-based controller. Our assessment of VAL as a platform, force control is really good. Well, overall, it's really nice to work on a robot that you're not scared to get within 10 feet of. We really like that while it's powered on. It's quiet also, so the people in the lab are happier. But it means that we can get near. It has a nice set of safety systems. NASA's pretty concerned about safety. So not only, they maybe don't have to have the same level of safety system on this robot necessarily as what they would do to send something up to space, but they do take the same level of safety for all their robot systems, whether it's going to space or station or not. So we feel really comfortable working closely with it. Where we want to tune our force control, we can go up and kind of push on the arm, where with Atlas we would never handle it directly, we'd go through a stick, and it decreases your ability to sense what's going on. We're able to be fairly stiff position control. We need to kind of evaluate the bandwidth more. Joint torques and speed seem reasonable to achieve what we'd like to do. Of course, with that, just like with Atlas, we'd like more knee torque. The knee is always a tough one to drive into a singles, especially a single. If you want to be able to do a deep knee bend, that would be great. So going up steps or double kind of cinder block height things, you really need a significant amount of knee torque, unless you're doing it dynamically. We'd like more range of motion, some of the sensing stuff like the LiDAR. Of course, we'd like a way to calibrate the joints and torque sensors, same with Atlas. Basically Boston Dynamics said, we'll put some tape on it and kind of just eyeball it, and we'd really like, hard stops or a calibration jig, a better way to make sure that the joints are where they say they are.
Peter, a question from Chris Atkinson. He's wondering if the SEA springs are back in the legs for your work?
Yes. Yeah, all the springs are back in VAL.
Okay.
Yep. And it's essential to have the springs for the force control. Other than the ankle, there's load cells on the ankle. It's a push-pull, kind of just like Atlas. It's two actuators for the ankle. And those have load cells, so you could take the springs out, but we put the springs back in the ankle as well. So it's now fully series elastic. And then we like that it's easy to assemble and disassemble, easy for maintenance, and it seems pretty reliable. and repeatability and reliability, you just gotta run it. You gotta put it through 8 hours a day, running it a lot. Safety is important because this robot is expected to operate close with people. So here it is responding to a push, so you can interact with it and it still stays stable. That's our push recovery with combined with our instantaneous capture point controller. But this is where NASA's headed with Mars. Might help with Mars exploration, assembling structures, exploring surroundings, set up and take down, and kind of maintaining the place while people are gone. And then some of the same overlaps with DRC, search and rescue and disaster. This is the areas of research, so our coactive interface, bipedal walking, of course, is important, planning. So we didn't do any kind of little dog type of planning that we did with motion planning. We would basically have the operator plan the footsteps. You create a set of footsteps with the operator review each one. With the little dog, we were able to analyze the terrain and create a path and search paths, which will probably apply to, we'll reintegrate back into our code base for the DRC, and as well as our work with this, we'll have a lot more automated type planning and footstep, terrain analysis and footstep planning. And then a little more telepresence. So with NASA, you deal with time delays from 8 seconds to 8 minutes, so it's a wide range of bandwidth and delays, so that's another way we're going to look at how to increase operator sense and operator control within those constraints. So these are some of the next steps we're going to do. There's some overlap in terms of goals with the DRC work, but then there's definitely some work that's exclusive to this project. And also getting feedback to JSC as to what to redesign. Where are some of the hardware issues, where are some of the sensing issues, what do you need to redesign in order to make this robot viable? Because we're really looking at doing a possible track D entry with Val for the finals. That would be our goal.
Cool. All right. Thank you. Any questions?
I'll try and answer as much as I can about Val-specific stuff, or, yeah.
If someone is just getting interested in working in teams like this, what kind of baby steps would you suggest that they take?
Learn how to program in Java.
What about hardware?
Hardware, just work with robots, become, mechatronics classes at your university. Learn encoders, different feedback mechanisms, load cells, learn EtherCAT. So we really like in our lab, we do all of our programming in Java. One thing we do when we have an applicant come and say, I'd like to do an internship, is we send them to a website to do a Java programming challenge. It's a way for us to assess their programming capabilities, because if you can't program, that's one of our key contributions. It's one way we basically develop is programming and Java, and Luca can attest to that. He's one of our interns visiting from IIT. You really have to be efficient in programming, and Java is our main language. But also learning some of the hardware stuff is important. We don't do as much, we don't develop hardware in the same way, but we work with hardware. So having that relationship is also important. So mechatronics, yeah.
Hey Peter, great talks. This kind of goes up for both the talks you had. Just can you make some comments on the role of simulation, like internal IHMC simulation versus VRC and anything else you might have? Yeah.
Super important. We use our own, we try and use our own simulator. We had for the VRC, we had to switch to Gazebo at the end, but we use Simulation Construction Set, which is our own dynamic simulator. The drawbacks on that is that it does not handle contacts well. It's point-to-surface contacts, but we're looking to develop surface-to-surface contacts. So hopefully the next month we'll be extending that. But the nice thing is that all of our controllers work, it's the same controller that we use in simulation and the hardware. There's some flags that we use to trigger different things in the simulation and on the robot, but it's really the same part, it's the same controller.
And are there any keys to trying to get the simulator to match? You talked about it's interesting, the slipping, trying to get the simulator to reproduce what the real world does.
The biggest is ground contact,
right,
and manipulating objects. Our simulation doesn't handle manipulation well, since when you want to grasp, it's more than just point to surface, it's surface to surface. So we don't do grasping in our simulation yet. That's really our biggest goal that we're working on adding. But other than that, especially all the geometric constraints, in the Little Dog project, it was extremely valuable because a lot of it was static, and so we'd use a simulator as a way to evaluate all the geometric constraints and ensure that things were working well. Yeah.
Would there be a NASA entry to the DRC using Val, or would Val just be through IHMC?
It's not clear. I don't know, but it might be a joint team. You know, whether it's NASA or IHMC or jointly, it's not clear yet, but it could be a joint, probably just a joint would be the most likely. But we would like to get Val up, you know, in the trials, in the finals.
I have a question.
Yeah.
So, I think I saw some visual signs of high latency and you're walking with Val. Do you know what your latency in the loop is? That robot?
It's, I can't remember, I can't recall, Luca, do you? It's, on our high level, we operate at about a 6, our high level controls are operating about 6 millisecond loop. And so it might be like 1 tick. Well, we can operate up to 6 milliseconds. We tried to speed it up when Boston Dynamics gave us a faster loop. We went down to the kilohertz.
Mm-hmm.
So then at 1 tick, we were, you know, a millisecond. So that's kind of where we prefer to be operating. Yes.
So minus the issues with the traffic shaping in the DRC, what was the expectation for Val's overall score?
6 to 8 was where we were looking at. And that's what we did in our preparation.
So suppose you have Val and Atlas, and you're allowed to play Frankenstein. What do you keep from each one? If you were going to build a new robot, what would you? Hydraulic base and electric top, or?
We don't know. We haven't fully evaluated Val yet, Frogs. We like the torques and speeds of hydraulics, but Val, we haven't fully exercised Val in terms of that. But it's close. We think that the performance will be close out of the actuators. But we haven't fully exercised it. Definitely like electric arms, because you don't need the same speeds, but having the compliance is much nicer. Yes.
Any idea on the operation time for the valve, with the battery pack that's on? How long will it operate? It is a battery pack, right? It runs off battery.
Yeah, battery. Oh, yeah.
So
It's a 2 kilowatt hour. I don't know. It's probably it's probably less than 2 kilowatts, so it's at least an hour of operation, especially depending on the task. Same with Boston Dynamics, but you can also go in lower power modes, because with electric, if you're stalling, like standing with bent knees, it's really bad. So if you're going into a mode, for manipulation, you're going to be manipulating for a while and want to save energy. You probably straighten your knees out and do tricks like that to save energy.
I gather that the computation on board is actually the limiting factor as well.
It's 3, so it's 3.
Because it's constantly ticking.
Yeah, we might reduce the number of computers. It has 3 i7s. Currently, the way IHMC is operating it, we have an off-board computer that's basically similar to the way Atlas was run.
Mm-hmm.
But we think we can use one of the i7s on board as our control computer. Or we'll have to trying to think of the rules for the trials, for the finals. But that's what we'd like to get, is to be fully integrated and untethered.
Okay, great. Well, let's thank Peter again.
All right, so now it's a lunch break. We're going to reconvene at